We go over another example, applied optimization. This time we're asked to find an optimal shape. This is one of those applications where we have to devise or design something so that the shape is optimal in some sense. Here we're trying to maximize area. So the problem says that there's a rancher um, who will use 600 meters of fencing to build a corral in the shape of a semicircle on top of a rectangle. We're asked then to find the dimensions that maximize the area of the corral. So we're trying to maximize what we can contain inside the corral, and given the specified restrictions that we have on the corral. I mean, for some reason, I mean, this is not important for the problem at hand, but the rancher wants to build a corral of this shape. Step one, I mean, remember we have to fix a variables, so the variables, you have to choose the variables that we're going to be working with. Here, this is the rectangle. This part of the rectangle is not included, of course, because we want to contain, I don't know, cattle or whatnot. There's no reason to not leave it connected. It just the problem meant that we have a circle on, I mean, semicircle on top of a rectangular shape. Here, so this is not part. So the dotted line is not part of the corral. So you don't know, you're not using part of the fencing here. So we have to set two variables. One, given that we have a semicircle, is one natural choice is r. R is the natural choice here, the first natural choice. So we have r for the radius of this semicircle. And that immediately implies that what we have here at the bottom is 2r, because it's parallel to the diameter of the semicircle. On the other hand, we also have the side, the dimensions of the side of this corral, but that is everything. So these are the only two variables. The rest, so for instance, the perimeter of the semicircle, the length of the semicircle is pi r, and this side here is L as well. Okay, so that's one thing. Now we want to maximize the area. The area in principle will depend on R and L. However, and this is something we've talked about before, we have some constraints. We have some restrictions. We have a geometric constraint here that we need to take advantage of. So remember, we know how to optimize or how to maximize quantities that depend on one variable. So in this case, we're going to choose, well, we can choose either L or R, but we're going to choose R. So, but since we have two variables here in principle, R and L, R and L, we need to find a way of using the restriction we have so as to express one in terms of the other. So what is the constraint? The perimeter the perimeter is equal to 600 meters. So we go back to the problem, and we notice here that Rancher will use 600 meters. So this is a constraint. I mean, if you could use whatever you wanted, then the optimization problem wouldn't have an answer because you can make it as big as you want. So the constraints you have just enough fencing for 600 meters. And the perimeter here, how do you compute it? Well, the perimeter, which happens to be equal to 600. Again, we drop the meter of the unit, and we can add it at the end. I mean, everything here is going to be measured in meters, square meters, or cubic meters. The perimeter is equal to, well, the three sides of the rectangle, this one, and this one of the rectangle, yes. So 2L plus 2R, and plus the length of the semicircle, which is pi r. So this implies then that 2L plus pi plus 2 r is equal to 600, which implies then that L is equal to 600 minus pi plus 2 times r over 2. So we've successfully reduced the problem to a problem where there's only one variable. So now we need, well, once we've used this, then we need to identify the objective function. So the objective function is the area as a function of r. So what is the total area? So the area of the rectangle is 2r times L. 2r times L, which is, well, we now know that L is a function of r, plus in the area of the semicircle, which is pi r squared over 2. Pi r squared over 2. But since we know that L is given by this expression here, then we may substitute that to obtain a function that can be maximized in a more convenient way. So because it depends only on one variable, r. This over 2 plus pi r squared over 2. Okay, so this is what we get. We get here r times 600 minus pi plus 2 times r plus pi r squared. This is in the end equal to 600 r, and we have minus pi r squared minus 2, minus pi r squared, and we have pi r squared over 2, so we're gonna get a minus pi over 2, minus pi over 2 plus 2 r squared. So this is in the end going to be our objective function. This is the function that we want to maximize. So well, now we need to identify the domain. What is the domain of our objective function? And like in most cases, the domain is found or can be prescribed by noticing that all the quantities in your problem have to be physical quantities. So first one, remember that we want to impose restrictions on R. So R has to be positive, right? Because the dimension R equals 0 doesn't have any meaning. and also L has to be greater than 0. Remember, we're using this restriction here just to give a restriction for R. So R greater than 0 tells you one endpoint of the interval where A is defined. L will give you the other one. Why? Because L, here, this condition here, is the same. Remember, the L is 600 plus pi plus 2 R. 600 minus pi plus 2 times R has to be greater than 0, which translates into R being less than 600 over pi plus 2. So R has to be greater than 0 and has to be less than 600 over pi plus 2. Remember, but those two come from physical considerations. So R has to be positive, right, to have a physical corral, and also L, the side of the the corral. If not, it's not going to have the shape of a rectangle in a circle on top of a rectangle. It's just going to be a semicircle. So the restrictions imposed by the rancher. So the domain is going to be so the domain is equal to the interval 0, 600 over pi plus 2. Okay, so now we have the domain, we have the objective function. What do we need to know? So we're again maximizing over an open interval. So we turn to the optimization problem. Okay, let's turn to the optimization problem. Now, so we look at what happens at the endpoints then. Endpoints. Okay, the function may not be defined at the endpoints, but computing the limits is going to be very easy because the function that defines a of r is continuous and makes sense even when you take on the value 0 or 600 over pi plus 2. So this is going to be the same as the limit as r goes to 0 plus, which is one of the endpoints of, and what is a of r is 600 r minus 2 plus pi over 2 r squared. So clearly this expression inside is continuous, so we can compute the limit by evaluating it when r is equal to 0. So this is just equal to 0. I mean, 600 times 0 minus something times 0 squared is 0. So now let's look at what happens at the other end. So we need to see what is the limit. The limit of a of r, but now as r approaches 600 over pi plus 2, and that is equal to the limit of the same quantity up here, so 600r minus 2 plus pi over 2 times r squared, as r approaches 600 over pi plus 2. But again, this is a polynomial, so it makes sense beyond where a of r makes sense. So this is just an expression that agrees with a of r inside the open interval. But now we take the limit, and this expression is continuous everywhere. We can evaluate this by simply plugging the value 600 over pi plus 2. So this is 600 times 600 over pi plus 2 minus 2 plus pi over 2 times 600 squared over pi plus 2 squared. And this is equal to, well, 600 squared is going to be a factor, common factor of pi plus 2 as well, in the two terms. 600 squared over pi plus 2 times 1, that's exactly the first term, minus, and I'm going to write this as a fraction, 4 plus pi over 2, and 600 squared is being factored out, and here we have 1 pi plus 2, pi plus 2. The other is being factored out, so we get that this is equal to 600 squared over pi plus 2 times, and the expression inside the parenthesis is 2 pi plus 4 minus 4 minus pi, all that divided by 2 times pi plus 2. We see here that we just get 600 squared times pi over 2 times pi plus 2 squared. Okay, so that's what happens at one of the endpoints. Now we need to look at our other candidates, so the critical points. Critical points here again, a is a polynomial of degree 2, so the only critical points that we will find are points where the derivative is equal to 0. If you differentiate a, you get 600 minus 2 plus pi over 2 times 2r, and if we set that equal to 0, we get 600 minus 4 plus pi times r is equal to 0. And this implies then that r is 600 over 4 plus pi. So up to this point, we have the values of a at the the limits of a as you approach both endpoints. Now we want to see what happens when you what's the value of a at the critical point, at the only critical point we found. So these are the only quantities that will tell us where there's a maximum or not, or because if the maximum among these three quantities is one of the limits of the endpoints, it means we can approach as much as we want, but we can never achieve dimensions that will be optimal. But if instead because this is an open interval, this is a function defined in an open interval. But if instead the critical point gives us the biggest value, then we're all okay, and that corresponds to our maximum. So what is a of r now? So at this critical point, a of 600 over 4 plus pi. Let's go back to the formula. So 600 times r, which is 600 over 4 plus pi. 600 over 4 plus pi minus 2 plus pi over 2 times 600 squared over 4 plus pi squared. Remember that it's r squared here. Again, we notice that we have a common factor of 600 over 4 plus pi. Now 600 squared over 4 plus pi. The first term is 1 then, when we factor it out, minus, and then I'm going to write this as 4 plus pi over 2. What's in this parenthesis here? And we get 1 over 4 plus pi. Right? This is the only thing that's missing here for 600 over 4 plus pi times something to become 600 over 4 plus pi squared. 600 squared times 1 is 600 squared. 4 plus pi times 4 plus pi gives us 4 plus pi squared, which is what we have there. But this simplifies very neatly for us. So 600 squared over 4 plus pi, and this 4 plus pi and this 4 plus pi cancel. We got then 1 minus 1/2, which is 1/2. So this whole thing is just equal to then to 600 squared over 2 times 4 plus pi. So this is the value of the area when you're at the critical point. So now let's compare. We have 3 quantities to compare. So 0, well, that's not. So now we compare. Here. So as r goes to 0, a of r goes to 0. So this is not a maximum. It is a minimum. I mean, the area can never be negative, so this is a minimum anyway. I mean, this approaches a minimum if r equals 0 was allowed, but it's not allowed. As r approaches 600 over pi plus 2, or what's pi plus 2? Let me see. What is the other endpoint? It must be pi plus 2. Yes, it's pi plus 2. So when we approach 600 over pi plus 2, pi plus 2, a of r approaches I forgot, it was I think 600 over 2 plus pi times pi, something of the sort. 600 pi over 2 times pi plus 2 squared. 600 squared over 2 times pi over 2 times pi plus 2 squared. And at r equals 600 over 4 plus pi. 4 plus pi, by the way, is in between, lies, if not, we will be finding a critical point that is outside of the range allowed for r, but this is in 0, 600 over 2 plus pi, or pi plus 2, which is the way we wrote it before. Why? Well, 600 divided by 4 plus pi is definitely greater than 0, and 600 over 4 plus pi is less than 600 over pi plus 2 because the denominator is bigger. Okay, so at r equals 600 over 4 plus pi, we computed the value of a 600 over 4 plus pi, and that was equal to 600 squared over 200 squared over 2 times 4 plus pi squared. No, or 4 plus pi, I'm sorry. 4 plus pi. So now we need to compare the only 2 quantities that make sense here. So this one over here, so this is the limit as we approach one of the endpoints, and this one. So which is bigger? 600 over 2 divided over 4 plus pi. I mean 600 squared. I'm sorry. It must be a square. Yeah, 600 squared, or 600 squared. 600 squared pi over pi plus 2 squared. 2 pi plus 2 squared. Which is bigger? Well, let's try to simplify things on both sides. So 600 squared, 600 squared. The 2's go away. 2's go away, and we cross multiply. So on this side, we get pi plus 2 squared, and on the other side we get pi times 4 plus pi. This is equal to 4 pi. This is equal to 4 pi plus pi squared. On the left hand side we get, well, the square of binomial. So pi squared plus 2 times 2 pi, so 4 pi, plus 2 squared, which is 4. We can cancel the 4 pi, and pi squared on both sides, and 4 is greater than what you end up on the right hand side. So 4 is greater than 0. So if we go back, it means that the left hand side has been bigger all along. And what did we have at the beginning? 600 squared over 2 times 4 plus pi, which is the value of a at the critical point. So the critical point gives a maximum. Gives a maximum value for the area for A of R. So the dimensions then, so in this way, the optimal dimensions for the corral are, well, we already know that R has to be 600 over 4 plus pi, and L is, well, we already saw that we already computed L in terms of R, so it's 2 plus pi over 2 R over 2, I believe. Let us check that this is indeed the case. So L is equal to, let me just see over here. Where can I find this? It's pi over 2. I mean by pi plus 2 times R. So all of that divided by 2. So it's pi. Let's go back to the end. So it's just pi plus 2. R, all of that divided by 2. That's what L is in terms of R. So if we expand, then we get 2 plus pi times 600 over 4 plus pi, all that divided by 2. So we get, well, we can factor then again by 600 over 2, and we get here 1 for the first expression, then minus 2 plus pi over 2, I don't know, I'm sorry, over 4 plus pi, and this is equal to 600 over 2, which is 300, times 4 plus pi minus 2 minus pi, all that divided by 4 plus pi. Pi's cancel out, we have a 2 here, so we end up with 600 over 4 plus pi. Okay, as we see, then our optimization problem was successful, so we can find dimensions within the allowed values for R, and the optimal dimensions are given by R being equal to 600 over 4 plus pi, where L is also 600 over 4 plus pi. One thing I would like to warn you about is this will not be always the case when you given an optimization problem that all the quantities are going to be the same, like in the case when you want to maximize the area of a rectangle and it's going to give you the square. That's not always the case. One way of breaking the symmetry, well, first of all, I mean, you can break the symmetry many ways, but one way of breaking the symmetry can come about when you are given a price to a certain size. So something is made of a different material, it costs a lot more than another material that you're going to use for a different part, then that's a possible variant, and that gives rise to completely different array of maxima and minima. Okay, so that's it for this video. I think we'll go over one more problem, and that should conclude, I mean, all the material for the final exam. I'm just gonna finish with a few tips. And if you want anything else, if you have any questions or any suggestions for problems you would like to see, I mean, see the solution to, just let me know.